Okay, so today we're going to talk about a different function group. We have already talked about the function group X, which is basically halogen alkanes. And now we'll talk about OH. That makes things, if it is as a function group, then it is called hydroxy. But if it is as part of the family, like the homologous series, then this becomes alcohol. So that's what this substance is. It makes alcohols. We know that the general formula of these things, provided that you don't have any rings, they are straight chain compounds, then the general formula, so this is hydroxy, and the general formula is CnH2n plus 1, which obviously we call R with OH. So ROH is the general formula for these things. Again, we are assuming that there is no cycles. If there is a cycle, then things change a little bit. There's no ring, there's no cycle. That's what happens. The name ends with ol, so at the end of the name, because they're alcohols, and this is the only or the most.
Sir?
Do you see it now?
Yes, sir.
Okay. So yeah, the name ends with ol, and that is usually if you don't have any more pressing uh, or any more important or more reactive function groups. In case of chlorine, it will stay alcohol. Okay, so that's the primary difference. That there is a hierarchy there, and you can easily find that in your book, the hierarchy. So if this is the most pressing function group, then this thing will be alcohol. Otherwise, it will work as hydroxy. Again, because this is functional group, it shows a lot of function group isomerism. For example, if I had 3 carbons, so it will be C3H7OH, but this compound can have, so as you can see, there are 8 different placements that I could have for the OH group. Now, 6 of them are going to be exactly the same. So I could place OH here, or I could place it here, 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 or here, and all of those will still be propane 1-ol. Okay, so that's prop 1-ol or propane 1-ol. But there are 2 places, 2 sites where I could put OH, this one or the one on the other side of this thing, where it will become prop 2-ol. So this is function group isomerism. Sorry, this is positional isomerism that this compound will show to us based on where the functional group is. As for function group isomerism, you can break OH into 2 parts. So for example, if I could break OH into O and H, then I could have something like this. Now this is function group isomerism. That was positional isomerism because I was changing the position of that thing. But this is functional group isomerism. And functional group isomerism simply means that all you have done, you have moved it from one point to another, and you have broken the functional group into 2 parts. And this way, you are able to make things that are not alcohols, but those are ethers. So ethers are easily formable, or you can easily make them as function group isomers of this thing. Okay, so that the one on the right, prop 1-ol, prop 2-ol, that is positional isomers, and this one is functional group isomer. Okay, so I hope that is clear. Moving on, uh, when do we classify them as primary or secondary? So primary alcohol, as you know, anything that is joined to carbon with 1 carbon next to it or no carbon next to it, that's primary. So prop 1-ol over here is primary alcohol. Similarly, a carbon that's attached to 2 other carbons is secondary. A carbon that's attached to 3 others is tertiary. And that is how you classify them as primary, secondary, or tertiary hydrocarbons. And that's how they're joined together. Okay, so for example, if I had a carbon here in which I have OH, of course, that's how it makes alcohol. So this is a primary right now. But if I had CH3 here, that's still a primary. This is secondary because it's attached to 2 carbons. And this is where it becomes tertiary because it's attached to 3 carbons. So that's how you get different kinds of primary, secondary, or tertiary alcohols with this. Okay, so that's the next classification. Uh, Now it's really easy to identify them. So इसमें कोई issue नहीं है ना कि मतलब secondary primary कौन से वाला होता है. You just have to look for the carbon that's attached to OH and how many other carbons is that attached to. It's really that simple. Why do we need alcohols? The most important use of alcohol is as a solvent, because alcohols are slightly acidic. We will study the properties, and depending on how big the molecule is, they have London dispersion forces as the primary intermolecular force, which means they can dissolve things that are not entirely soluble in water. They also have the OH part where things can form hydrogen bond. So they do dissolve things that are soluble in water to some extent. And that is why, depending on the size of the molecule, we can use them as solvents. Second primary use of alcohols is when you want to make esters. So we use them to make esters because esters have a big application in the industry. Uh, those fruity smelling things. We use them for flavoring. We use them for different smells. So they're really useful for that. So these are the two major applications or uses of alcohols. Now, again, as a solvent, there are two parts there. There's the one that is able to form a hydrogen bond, OH, and then there is the other non-polar part, which is able to form London dispersion forces. And that's the main difference between alcohols and alkanes, because you can have liquid alkanes, but they will only have London dispersion forces, and these ones will have hydrogen bonds as well because of the polar tail. We call that a polar tail. Same thing, because of their ability to make uh, these hydrogen bonds, they have higher boiling point than other uh, organic compounds that have similar MR or similar number of carbons because of that polar tail that they have. So, for example, methanol, uh, this is just one carbon and three hydrogen and OH, so CH3OH. This is quite similar in structure to methane, but methane is a gas which has a very, very low boiling point and melting point. But methanol is a liquid at room temperature, which means its boiling point is higher than the room temperature. That's a big difference. That's a big difference of almost 100 degrees Celsius or more. And again, that is only because it has a polar side. It has this OH in which there is obviously the lone pair. So if I were to draw it correctly, then I have a lone pair here, and there will be a bent structure here. There's going to be 109.5 as the, 104.5 as the angle. And because of that, this is able to form these hydrogen bonds, which means if I had another methanol molecule, then the H positive and slightly negative hydrogen, they can form these. So if I had this, then the lone pair on this oxygen will attract this hydrogen and that will attract this hydrogen. So that is going to form some sort of a lattice, some sort of structure, which is not possible in methane or other things. So alcohols easily mix with water also because of this reason, because water has H2O, and that oxygen in water has a lone pair. It's in a polar bond. So water is also able to form hydrogen bonds with small molecules of alcohols. Again, the bigger the non-polar part becomes, like if you have like C7, then what happens is that you have a big part of the molecule which is non-polar, which is unable to form hydrogen bond. So that alcohol will not dissolve in water. So it's a misconception that students have that all alcohols dissolve in water. That's not the case. Only the small molecules are. And again, the reason is that in small molecules, the primary formation of hydrogen bond is quite strong, and they can allow them to dissolve in water. Larger alcohols will not dissolve in water. Again, we have already talked about that the boiling points are higher, melting points are higher than other things of the same MR, comparable MR. And the reason is again, because hydrogen bond. So you need more energy to break them. Same for solubility. Uh, Alcohols like methanol or ethanol are highly soluble, or because they are able to form these hydrogen bonds with water. But hexanol, for example, is only slightly soluble. So it will dissolve to some extent and then it will form a layer, it will not dissolve. That itself has some applications that we study in A2, especially in partitions. But other than that, if you get larger alcohols like decanol, they will entirely not dissolve in water because they are unable to make hydrogen bond. There's a primary force there It is the London dispersion force that is the primary force there, which is why it will not dissolve. Okay. Next, there is a chemical property which all alcohols, in fact, all organic compounds have, that is combustion. So alcohols, like other organic compounds, will burn and they will produce carbon dioxide and water. So if I have ethanol, then it will burn in excess oxygen, producing carbon dioxide and water. Now, here's an important idea. Because you already have one oxygen in there, you can cut that as a slack when you're trying to balance it out. So over here, I know there's two carbons, so I'll produce two carbon dioxide. I have uh, this thing, H5OH. Let me break it down into a more manageable way. I can say that I have H4 and HOH. This way, just try to understand that one whole ingredients for one whole water molecule are just coming from within the compound, the alcohol itself. Of course, that's not correct as far the structure is concerned. It's not H and OH that is in there, but you can still think of it that you are getting one entire molecule being made from things that are part of the alcohol, which means that I just need to make sure that I have 4 hydrogen. They will make 2 water, and I have one more H and OH, which will make the third water molecule. So basically, I'm getting 3 water. So it makes it much easier to balance equations like this. How do you think about it? Think about it that you have H and OH, and that's one water molecule that's separate, that's already made. And whatever you have left, like 4 hydrogen left, that will make 2 water. So total 3. Let's try another one. Let's suppose I have C3H7OH. Now again, think about it that you have, so of course, यहाँ पे oxygen को तो balance करना होगा. 2 times 2 is 4, 4 plus 3, 7, 7, and this 7 by 2. Yeah. No, not 7 by 2. I already have 1 in there, so this is 3. Okay. Just like that, you have C3H7OH, so they will make 3 carbon dioxide. But how many water molecules? Again, I have 1 HOH already, that's 1, and then 6 hydrogens left. So 6 makes 3. So 3 plus 1, 4. 4 water molecules. Okay, so I'm able to make 4 water molecules. And this gives me what? 3 times 2, 6 plus 4, 10. Wait a minute, is that correct? Yeah, it is correct. And this will give me 9 over 2. And then 9 over 2 times. The whole thing can be multiplied by 2 if you are more comfortable with those numbers, giving me 6 CO2 plus 8 H2O. Yeah, here you go. So that is combustion of alcohols. Now, let's talk about the other chemical reactions. Alcohols, again, they have H positive that they can lose because the hydrogen oxygen bond is polar, just like water, just like other alcohols, other acids. So what's going to happen? You have, let's take ethanol, C2H5OH. Now, what we do already have is slightly negative. Sodium being a very strong reducing agent. It's a very strong reducing agent, which means you don't even need to heat this thing. You just put sodium in, and what will sodium do? Sodium will give its electron to hydrogen, which is already electron deficient, which is already slightly positive. So sodium will give its electron to it, and what will that do? Hydrogen will make hydrogen gas. It takes electrons, it is reduced. And what happens to sodium? It makes sodium ion. And now C2H5O is the negative charged ion. It's an anion, and sodium is the positive charged ion, cation. And this is what we call sodium ethoxide. This ion is called ethoxide ion. Okay, it's an ion just like nitrate, just like carbonate, that has covalent bonding in it. You have seen these before. You have seen carbonate, you have seen nitrate, sulfate, all of them have covalent bonding. And just like that, this is a new kind of ion which has covalent bonding in it as well. So you could, नई चीज नहीं है. And just like वहां पे, we would, if this was nitrate, we would say sodium nitrate. So यहाँ पे we'll say sodium ethoxide. And obviously hydrogen will balance it out. Okay, so think about it like this. Whatever water did in inorganic chemistry, most of the time, alcohols are going to do the same in organic chemistry. Alcohol is like the equivalent of water in organic chemistry. वहां पे हम देखते थे कोई चीज वाटर में सॉल्युबल है या नहीं है, यहाँ पे हम देखेंगे कोई चीज एथेनॉल में सॉल्युबल है या नहीं है, ठीक है, या एल्कोहल्स में इन जनरल सॉल्युबल है या नहीं है। सिमिलरली वाटर में सोडियम डालते थे तो क्या होता था, इट वुड गिव सोडियम हाइड्रोक्साइड। वो हाइड्रोक्साइड क्यों था, बिकॉज वाटर had AH and OH, and when sodium reacted with it, there was a slightly positive bond here, slightly negative bond here. What happened, sodium went and displaced that, और हाइड्रोजन को वो इलेक्ट्रॉन पकड़ाता था और वो भाग जाता था, and this way you were able to make sodium hydroxide. The only difference now is that instead of having hydro, the hydrogen part, you have ether. That's it, you have two carbons. So this is nothing new, this is something we have already seen. वहां पे जो वाटर करता था सोडियम के साथ, यहाँ पे अल्कोहल करा, and it's happening at room temperature. हाँ, alcohol will be slower, water will be faster. That's it, that's it. So this is a principle that will really help you out throughout organic chemistry. So I'm going to give you a question. I want you to complete this equation. So let's suppose I have, so I have this equation. So what's going to happen here, again, the only thing that's going to change is that you're going to get sodium instead of this hydrogen. No other hydrogen is going to do that. The reason, because the bond is not polar. Between carbon and hydrogen, the bond is not polar. So no other hydrogen, even though you have so many hydrogens available, none of them will take part in this reaction. Only this OH wala hydrogen will. And that's why you're going to get sodium butoxide here. So this will go like this negative and this sodium positive. That's how you write it. So sodium butoxide, okay, or but2 oxide. Similarly, this one, both the hydrogens will be removed and they will form hydrogen gas. So both the hydrogens are gone, both the oxygen get negative charge, and then sodium is attached to both of them. So this is sodium 2,3 butoxide or sodium but2,3 oxide. Okay, so that's how you make this thing. Obviously, you're going to get hydrogen as the byproduct in both. So one observation that you'll see, bubbles of a gas that pops in a flame. Okay, so that is how you can use salts and displacement reaction using sodium. Obviously, potassium will do the same thing. Okay, so that's one. Now, what other reactions can you do with alcohol? Alcohols are very versatile. And that's why there are many reactions that we need to know about. Okay, so one reaction that we do is, if we have alcohol, is there a way to dehydrate it? Like, can we remove water from it? Because remember, how did we make alcohols? One important way of making alcohols was that you took alkene, you gave it water at 300 degrees Celsius. Of course, it becomes steam over there. In presence of in presence of a catalyst, phosphoric acid. And what happened was that water will add to alkene, break the double bond, and you were able to get alcohol. So now we are going to reverse that process. So alcohols can be converted to alkenes. This is the reverse process. So alkene to alcohol, we know that. Alcohol to alkene, what do you need? You take the alcohol that you have. It's going to do a dehydration process. It's also an elimination reaction. Okay, so you need concentrated sulfuric acid, 200 degrees Celsius, and aluminium oxide catalyst. Again, aluminium oxide is very good at absorbing water. Okay, so that's why we use it. Sometimes we also call it ceramic wool, in which we dissolve it. So that way, aluminium oxide is going to form that ceramic wool. So you could do two things. You could either use sulfuric acid at 200 degrees Celsius, or you could use aluminum oxide at 350 degrees Celsius. Both of these will work, one of them. And what will happen, it will convert it to alkene and remove water. So let's take an example. Let's suppose I do this, I give it the required conditions. And what happens is that this OH is removed from one carbon and H is removed from the other carbon. Remember this thing, it's not hydrogen and hydroxide being removed from the same carbon. It's OH from one, H from the one next to it, right next to it. So which means that you have a chance of making cis trans isomers using this whenever possible. Okay, so that's something that can happen. So here you go. We remove this, and now you have a double bond here, and there you go. This is propene. Okay, and of course H2O is the byproduct here. Again, one of the two conditions. Now, one diagram that examiner usually gives us for this is this one. So there's a, wait a minute, I might have it here somewhere. Let me copy it from your book. So look over here. You have ceramic wool soaked in ethanol. It is wool that ethanol is dissolved in because we want to make sure that ethanol has a larger surface area to evaporate. So it evaporates, goes over the pumice. Pumice absorbs water much easily, and it's like a network in which this alcohol uh, will have to pass through, and because it's hot, it will give heat to those alcohol particles. Now it does the reaction, and then you pass it over, and it is collected over water. And why are we collecting over water? Because they're insoluble, so we can easily collect them over water. Okay, the examiner does not ask you about pumice or why is it soaked in ethanol in ceramic wool or anything. They don't. You just need to identify that as long as you have these required conditions, you will be able to remove H and OH from an alcohol particle. So we have already seen this when we were talking about alkenes. And again, as I've told you, there is a chance of making isomers. So let's put that to a test. Let's try to solve this equation. Let's suppose I have this alcohol and I do it 350 degrees Celsius, Al2O3. Go on, make two different compounds that can be made from this.
So first one is water.
Of course, we get water in both situations. I'm just saying,
Yeah.
what two isomers are we going to get? We are going to get butane in both cases.
But1ene.
Good, that's one option. And in that case, you're removing this hydrogen and hydrogen from this one. So that is one option. But1ene, good.
And but2ene.
Butene, yes, exactly. Because in that case, we'll remove OH here, but hydrogen from the next carbon on this side. And that will give me butene. Now, the thing with butene is that it can make cis trans isomers, because let me redraw butene. If you look at butene, then what you have is a C double bond here. On one side, you have CH3 on both of them and hydrogen. So as long as the two carbons are attached to different things, they can make cis trans isomerism. So this one is cis because if you notice, CH3 is on both sides, on the same side of double bond. And you can also get trans in which this is the case. So technically, you're going to get three different isomers. One is but1ene, one is butene, one is cis butene, and then trans butene. So those are the two other options that we have. Now, in halogen alkanes, we saw one reaction, which was that you could replace the halogen in the halogen alkane with OH. And for that, we did alkali in water. So if we were doing that, and obviously we heated it in a flux, then we were able to convert a halogen alkane to an alcohol. Now, how do you reverse that? So again, that's really easy. How do you reverse that? You need something that will provide the halogen. And what better thing provides a halogen than an acid, right? So you take a halogen acid, it could be hydrogen iodide, it could be hydrogen chloride, it could be hydrogen bromide. And what you do is that you take the alcohol. So this reaction is alcohols used to make halogen alkane. So what we are doing is we are replacing OH with a halogen. Okay. And of course, this is OH minus is being removed and I minus or Br minus or Cl minus is coming in. So you are basically replacing one nucleophile with another nucleophile. So this is nucleophilic substitution reaction. So here's how it goes. I take an alcohol, again, I'm taking ethanol, and I add HBr to it. Now, again, I need it to be concentrated because I need it to react completely. And because I know that alcohols are volatile, I will basically give it heat under reflux. And this is a really straightforward reaction. I'm going to get this OH replaced with Br in this case, and that H positive from HBr will react with OH and make water. And there you go. But what if I don't want to use HBr? I could use any other thing that's going to give me Br. So I could use sodium bromide, or I could use just bromine atom as well, bromine molecules as well. But people have seen that there is a specific combination of catalysts that works for them. So for example, if you have the acid on its own, HBr, you can just use it, or you have HI, or you have HCl, you have concentrated solution. It will directly add and it will make the halogen alkane. But if you don't have that, and there's a chance that you will get something else like sodium bromide, or you will get a bromine atom, a bromine molecule itself, then those things, if you are using pure halogen, then we add it with red phosphorus. The red phosphorus is an allotrope of phosphorus, and we use it as a catalyst with pure halogen. So if you want to add bromine, you make sure you add it with red phosphorus. Or if you want to add iodine, you do it with red phosphorus. Then if you want to use any salt of halogen, if you have like sodium bromide or sodium chloride or sodium iodide, then we usually use concentrated sulfuric acid for that. Again, I'm looking for a strong acid, and sulfuric acid is a very good acid for that. Again, I could use the acid itself, HBr, HI, HCl, but if I don't have it, then I just use the H2SO4 as an acid and sodium salt as the uh, nucleophile providing component. So we have three different cases, and so here's how it goes. You can either take the hydrogen halide salt, the acid itself, and if it is an acid itself, it's going to work as acid, it's going to provide nucleophile. And both of those things are being done by HBr or HI or HCl, whatever you have. But if you're using pure element, then because pure elements do not have polar bond, it's not that easy to make nucleophile for them. So to do that, we use a catalyst. And for that, we use a red phosphorus. If you have sodium salts, then you use concentrated sulfuric acid, and that can also produce the same thing. Technically, what's happening? Technically, sodium oxide will react with H2SO4 and produce HX. So sodium chloride will, with sulfuric acid, will produce HCl. There's a chance it will. It's not as strong a chance as is the sodium bromide producing hydrogen bromide. So I take sodium bromide, I react it with sulfuric acid. Sulfuric acid gives the H positive. Sodium bromide gives the Br, and I'm able to make HBr. That HBr then reacts with ethanol and replaces OH with Br. If I use sodium iodide, that's even faster because I can use sodium iodide. The bond is weaker than sodium bromide. I react it with sulfuric acid, and that hydrogen from the sulfuric acid and the bromide from, iodide from sodium iodide react, makes HI. That HI will come in, react with ethanol, make iodoethane or ethyl iodide. So that's again. So the point I'm using salt with concentrated sulfuric acid for is because sulfuric acid breaks down readily, gives me the first H positive. Of course, it has two H positives, but we have seen in Ka and equilibria that sulfuric acid gives the first hydrogen ion foreign, and the second hydrogen ion takes a while. So that's why when concentrated sulfuric acid reacts, it gives the first hydrogen ion right away, which forms the HX, which then reacts to make halogen alkane. So with alcohols, that is a combination that we could use. Okay, so that's an important reaction to remember, that how do you convert alcohols to halogen alkane. So as I've told you in the beginning, alcohols are very versatile. So far, we have seen how you can make alkenes from them. We have seen how we can make ethoxide salts from them, alkoxide salts. And now we have seen how you can convert alcohols to halogen alkanes. There's one more reaction that we will do today, and tomorrow we'll talk about. So these are all the reactions, first kind of reaction for alcohol, in which you produce some other family from them. The last one of this kind is alcohol being converted to ester. And this is something you have seen in O levels as well. What you did not see over there was what was the catalyst. Otherwise, it's exactly what you have seen in O levels. The catalyst, I'll just tell you, it has to be concentrated sulfuric acid. And we usually give it 60 degrees Celsius. Of course, alcohol on its own won't do it. You need a carboxylic acid to react with it. So you take the alcohol, you add the carboxylic acid. And the reason you're doing this is because you want to do a condensation reaction. Alcohol will provide H or OH, and acid will provide H or OH, and they will react. Analysis has shown that most of the time when this happens, alcohol provides H and carboxylic acid provides OH, but it doesn't matter. It honestly doesn't matter at this stage. So you're going to get ester, and the byproduct is water. So why is this reaction different from the one that we saw for alkenes? Because in this reaction, you are removing H and OH from different molecules. H is coming from alcohol, OH is coming from carboxylic acid, and that's how you're able to make ester. So what was happening in the alkene wala reaction? You were removing H and OH from the same molecule, which is why that reaction was called elimination. So elimination is when H and OH, or it could be NH2 and H, any small molecule is removed, but both the things are coming from the same molecule, that's elimination. And both the things coming from individual molecules, different molecules, that is uh, condensation. You can also, by the way, think of condensation as nucleophilic substitution. So that's also one option that you can consider this. Okay, so we have seen how you convert alcohols and use them as feedstock for many different families. You can make esters, you can make halogen alkanes, you can make alkenes, you can make ethoxides from them, or alkoxides basically. And of course, you can burn them. So these are the two main reactions that we've seen today. We have two more to go. So we will do that in the next class. And of course, I will spend the classes after that, a good number of classes on practicing questions, because alcohols are super important because they pave the way for carboxylic acids. And they are the third major family of compounds after hydrocarbons, halogen alkanes, and alcohols. These three are the pillars of organic chemistry that you need to understand. All right, so see you